I hope you'll hear me, I'm not sure. Hello, my name is Alexandra Ene, and we represent Technical University from Civil Engineering in Bucharest. Last year we were in a student RICVA competition, and we won the third prize. Now we would like to share with you our experiment there and how we felt during this competition.
Good afternoon, I am Claudiu, STANCIU, and today we will present you the project entitled Innovative Acoustic Approach for Building Air Permeability Estimation using Experimental and Numerical Study.
I'm in my second year of my master's degree, and until this moment I was involved in the national and the European research project, through which I managed to write several articles on acoustic comfort.
I am a member of Over 4 project, which represents next year Romania at Solar Decathlon in Hungary, and during the last year I was involved in multiple technical projects.
So, air infiltrations can have a powerful impact on several parameters inside a building that are influencing the energy consumption. Only the air infiltrations can lead up to 50% of the heat losses through a building. It can have also an impact on indoor air quality. And by means of that, we're referring to pollutant transport, higher velocities, or moisture problems. It can have also an impact on acoustic comfort, and by means of that, we're referring to noise propagations, and on the long term can lead to health problems. So there is a major need to estimate correctly the air infiltrations. At the moment, there are several possibilities for determining the air infiltrations, either that we're choosing the predictive models, but this can lead to errors up to 100% for some cases, which would be unacceptable, or we can choose an experimental approach like the blower door system, but this is weather dependent, is time consuming, and requires large and expensive equipment. On the other hand, the tracer gas method not only that requires more complex and expensive equipment, but also requires a special gas with certain properties.
So, is there a compromise solution between inaccurate prediction models and the more complex experimental measurements? The answer is yes, a novel acoustic method. We want to prove the correlation between sound and air transfer phenomena, and we develop an easy tool to quickly estimate air permeability. The experiment was conducted in a full-scale experimental facility at National Building Institute of Research in accordance with the European norm 717. The stand was formed by 2 rooms, structurally dissociated, and we studied the sound and air transmission to a windows placed in the middle of the facade. We placed 5 sonometers, the sound sources and the blower door system in the emission room, which is seen like outdoor environment, and another 5 sonometers in the reception room, which is seen like indoor space.
During our experimental approach, we were interested in 9 different types of windows using different frame materials like wood, aluminum, and PVC. And we were interested also in 8 different windows apertures. As you can see in these figures here, case 1 with the window sealed, meaning no air infiltrations, case 2 with the window semi-sealed, case 3 with the windows normally closed, and 5 different windows apertures. So in the end, we can say that we had carried out 144 complex experimental campaigns.
The equipment that we used for the experiment was a blower door system, a computer, and a test of 418. We only use high precision equipment, which is help me please. We only use high precision equipment that prove for our quality and complexity experiment.
As for the acoustic part, we used 2 sound sources, several sound meters, 1 multipoint station, 2 computers, and several softwares for downloading and recording the data like Measurement Partner Suite or LabShop. and the measurements were conducted in accordance with the European norms.
We conducted two experiments, permeability and acoustic, and here you can see some images with us. For example, me installing the blower door system. Here is the reception room and us preparing one of the cases, and their emission room. Here is my colleague Alexandra downloading the data from lab shop software, and me preparing the couple wood pane window. Regarding to this experiment, we followed the next three steps for determine the permeability of facade. The first step was to determine over and under pressure. The second one was to determine the average permeability law. And the last one, the third step, was to extracting the facade permeability law from room law. Here it's an example of single wood pane windows with facade permeability for each case in a range of 4 to 70 pascals. We are interested just in 4 Pascal area. In the right graphic, you can see the effective leakage area, which is growing as the window aperture is higher.
As for the experimental acoustic part, first of all, we determined the sound pressure level difference between the emission and the reception room. And here you can see only an example for the simple wood pane window. We can see that as the joint surface is growing, the sound pressure level difference presents lower values. Further on, we determined the sound reduction index for a range of frequencies between 100 and 5000 Hz. Here it's only an example also where we highlighted the simple wood pane window, and for the frequency of 500 Hz, we can see that as the joint surface is growing, the sound reduction index is dropping. So, in order to obtain the correlation between air and sound transfer phenomena, we had to go through more than 1 million values. Only a small portion of these values you can see in this graphic here, where we highlighted again the simple wood pane window. And we're proposing through this method that by only measuring the sound pressure level difference between the outside and the inside of a facade to determine the airflow. Due to the fact that during the experimental approach we determined the sound pressure level difference with a room that presented a reverberation time of 5 seconds, now we were interested to lower these values and to see the impact of other reverberation time on the sound transfer phenomena. This was done only by a numerical approach by using Odeon software, but first of all we needed to calibrate the model to be sure that we're receiving the same answers. So this was done by following the 5 steps that you can see written on the slideshow right now. Although calibrating the model didn't sound that difficult at the beginning, it has proven to me the most challenging and difficult part of this whole research. And in the end, it was successfully done, as you can see in this first graphic here, presenting errors less than 1%. The second graphic shows the impact of other reverberation time on the sound transfer phenomena. And we can see that lower values of reverberation time can lead to higher values of the airflow.
So throughout of our experiments of 8 months of work, we carried out 144 experimental cases, 288 simulated cases, and 36 curves, as you can see in this graphic. We determined 4 models for each reverberation times by means of data feed model, and translated it in a 3D representation by means of MATLAB software. But it's still difficult to read this nomogram, and as a solution we created an easy tool to determine the airflow that has as input sound pressure level difference and type of the window, and as outputs, of course, the airflow.
So from the scientific point of view, we can conclude that we have obtained a correlation between air and sound transfer phenomena and moreover a nomogram to prove the innovative character of our research. On the other hand, from the technical point of view, we can conclude that we have obtained a tool which is not weather dependent, is not time consuming, requires less and inexpensive equipment, and it has a good precision because it's an experimental approach to determine the air permeability of a facade with high necessity in real estates, purchasing and renting, thermal rehabilitation, and energy certifications for newer and older buildings.
Thank you for the attention.
Thank you very much. It was quite innovative, new and interesting, helping engineers to do their work on building energy audits much easier with your method. So my question is, are you going to patent it or maybe?
This is only the beginning. We had the idea, we managed to do the experiments into a laboratory, but it's still at the beginning. We need to improve our experiments, and we hope that we're gonna do this soon. We're on our way to, I hope.
Thank you. Do we have questions from the audience, from our students? If not, then thank you once again for coming and presenting this very interesting research you've done. Thank you once again. And I will call our next